Okay. So we'll study today how TCP works. Okay, and we'll leave it to you to study UDP, because UDP is very simple. If you understand TCP, then you can understand. It's very elementary to understand UDP. Possibly most complex protocol. Of course, IP is also. See, I can say very simple. What we studied is simple, but if you consider with IP or routing protocols, you know how routers exchange information like BGP and other protocol, then it becomes little complex. So we have not done that part because it's really complex. And secondly, of course, there are some security issues when the routers exchange information about routes, but it will take 2-3 classes to teach you how all these protocols work. So possibly had you done networking course, we would have possibly taken up those topics. But anyway, this is a very basic course, so we'll skip that. However, let's so today's talk is about transport layer, and next class we'll look at what are the security holes or security vulnerabilities in TCP, and then we will study secure protocol that all of us use today in browser, which is called TLS, or earlier it was called SSL, right? All right. Every browser has this feature of TLS. Okay, so the best book to read this, of course, is Kuros and Ross, and of course, I have taken lectures from contents from this lecture as well. So these two are lovely places to read about TCP. Okay, so the question is that this diagram we have seen, right? And there's ATM machine. Do you think this has more security or this? Which one? So this two I found, right? So I thought, which is more secure? Where in first case, Mr. Guard is sleeping. Second case, dogs. Dogs are supposed to protect, right? And they are also sleeping. I will
Second
leave
one.
it to you to answer. Okay,
First one.
think about it. Well, depends on what is your threat model. Okay. So again, we'll repeat internet, because this is, if you go to interviews and most likely something or other would be asked on internet if you attend interviews of companies like Cisco or Brocade, Juniper, whatever, right? Even Google, right? Because their business is based on internet. Internet is a network of network, that we understood, right? I mean, network is of type, say, LAN, local area network, or it could be any multiple LANs connected with routers and so on, right? And then they are connected through router. At the edge, you can always see a router, and these router exchange information with each other and find out the routes, because IP address is kind of structured address. Okay, IP address of companies in, or you in Bangalore would be different from IP address of people in New York, or even in different parts of India, right? Okay, based on this hierarchical addressing, packets route, because all these routers exchange information, because they will decide if the IP address is something, then where to send it to, right? And note that always message travels from one router to another router, like here and here to here and to here and so on. All right. Okay. And then we have seen IP is connectionless. This is an unreliable best effort protocol. Unreliable means that IP simply says that I don't care. I mean, if packet is, if I'm not able to deliver the packet, I will drop the packet. But I will make my best effort, right? So there may be routers on the way, like here, some routers may be congested. Okay, a lot of traffic is coming in. Then its buffers are full, and then packets will be dropped. Addressing, we know, is a numerical addressing which has some structure. It's not flat. If it's a flat addressing, then you can't send. Routing is very, very difficult, right? Only in a small domain like your classroom, if your names are unique and there are about 30 students, then you will remember each other's name and you can do routing within yourself, within your classmates, right? If imagine even IT Mandi must be having 2000 students, and by first name you cannot do transfer of information, right? Then you need complete address, the, for example, Suryansh is of some hostel and some room, and name, room number, and hostel, that becomes hierarchical, right? Then you can communicate within each other within the campus, right? All right. So typically routing takes several hops that we have seen, and we have seen the packet, there is source ID, destination ID, etc., etc., right? All right. Now IP is unreliable. Reliability, see, reliability, it means that if I have a information to send and I put this inside IP packet, it reaches to other end as it is without even a single bit of error. So whatever you send should reach to other end, right? Okay. On the way, if this packet goes to router should not drop the packet. Okay. Now you imagine you're transferring a file from machine A to machine B, okay, over internet, then not even a single byte of the file can be an error. Otherwise, file will not, is unusable, right? Okay. So now IP does not guarantee any of these. Now IP packets generally have a small checksum, an error correcting, error detecting code, right? But these are unkeyed. That's first thing. No, we don't use symmetric keys kind. And secondly, just single bit of error, a few bits of error we can find out. That's it. Okay, nothing more than that. Okay, there is no cryptographic MAC. We use MAC for integrity plus authentication. Anybody can make IP packets and with any IP address and send it to other end. Okay, so IP is unreliable and best effort, that we know. All right. Okay, just a minute. Okay, all right. So packets may be lost, packet may be corrupted, packets. So we have seen that in case of IP, packets may be lost on the way or dropped by routers. Packets may get corrupted by routers. I mean, routers or in the link over which it goes, there is a possibility that few bits may get flipped. Okay, or packets may deliver out of order because source is sending sequence of packets, and packets may take different route. Well, understanding between router changes, so packets may reach at different times, of course different times, but may take different paths. So first packet may reach second, and second packet may reach first, and so on and so forth, right? So now this can be an issue that how you are going to assemble them, because your file, one after other, if you're taking the content and sending in a packet, they have it, the file must be reassembled back, right? Now there must be some way for reassembling back, right? IP does not guarantee any of this. Okay, so it is left to higher level protocols to ensure that connection is reliable, if you want reliability. Now some people may say that most of the time, most of the packets reach in order, right? So if something reaches out of order, you can just drop it. Like in your, for example, you're having streaming protocols, like you get OTT IPL matches and some packets are dropped in between, doesn't matter really. Although nowadays most OTT also use TCP, right? So we need some way for reliability. And second thing very important is that See, IP address belongs to what? IP address belongs to the machine or interface, okay, or computer. A computer may have is not running a single process, right? It may be running in hundreds of processes, right? Process is nothing but programs that are in run, right? Programs that are running. For example, you can have when you're streaming data from other end, so there is a protocol running, right? A TCP basically running in some form for your Netflix or whatever. Okay, so now when you receive IP packet, this belongs to the interface here or the machine here. That's where IP packet will give, right? Then how machine can send it to a particular process? For example, you are streaming at the same time you are reading emails, okay, or at the same time you are doing file transfers, right? So multiple packets are coming, so some way it should be sent to different processes, when different packets come. First packet may go to first application, second may go to second, third packet may go to third, and so on, or some way. How do you know incoming packet is for a particular process? Any idea about it? Anyone? What do we use for that? For
Port number,
example, yeah,
uh,
go ahead.
port number for the processes used.
Yes, absolutely. Like, for example, your IP address is your home address. Okay, and somebody sends something, then it will reach home, but there has to be something to tell that is for your father, mother, you, your sister, or somebody else. Okay. Similarly, here we use something for delivering to different process within a machine. Okay. Now let's come to that point which you have just mentioned. IP protocols is basically node to node delivery between one machine to another machine. Okay. If there are multiple applications running, then packets that has come has got to go to an appropriate process, right? Because this, see, some application at the other end is also trying to communicate, so is trying to communicate to a particular application here, a particular process here. The packet has to be routed to appropriate one, right? And similarly, if there are multiple applications that are sending packets or multiple process sending packet, they must also go over the same link, right? All right, so there must be some way to tell to other end that which particular process is sending this. Okay, so we call this demultiplexing. When a packet comes to a node and it has to be sent to appropriate app or process, this is called demultiplexing. Multiplexing is that when packets are coming processes that it has got to go in single link. So that's called multiplexing and demultiplexing. So we use ports and something called sockets, right? You would have done socket programming. Okay. Now when you write a program, then you create a socket, do the transfer, and in order to create a socket you have to use a port number which is free and available. Okay, and then fill the data in, and then when data transfer is over, close that socket, right? So you would have done that, right? All right, so multiplexing, demultiplexing is shown here, that packets are coming, this corresponds to IP address. Okay, and then it has got to go to appropriate application, right? So we are doing demultiplexing here in the sense that if port number is corresponding to the application running here, it will go here to this one. Suppose you are using two browsers, then this browser also using some port, so it has got to go to this particular app, and so on. Okay, this is a mail, so this will use different port. So the packet that is incoming will clearly define what is the port here, destination port. Okay, now where is it? It's not part of IP. It means that now this port number etc. have got to be part of higher level protocol. So if this is IP packet, inside this will be TCP packet or UDP packet, and then this will also have a header, and this header will define where this packet will go to, right? So this is demultiplexing and this is a multiplexing, right? It is simple. Okay. So port is transport layer identifier, which is 16-bit. Okay. So packet carries both source and destination port numbers. Okay, and this helps us to differentiate where the packets will go to, right? Or all right. Now, what are these port numbers? You create a new application, then there are port numbers which are available, freely usable, right? And if nobody is using it, then you will be assigned that port number and then can use it. Okay. On the other hand, there has got to be some port numbers which everyone wants to talk to. Say, for example, HTTP. You know, you are running a browser and is doing HTTP with server. Then this server, this HTTP program in server is running at port 80. So some of these ports are well known and don't change. So it's a well defined by IETF or somebody. Okay. All right. So these points we have already seen, already discussed. So there are well known ports like 0 to 1023. These are well defined by organization like SSH is 22, HTTP is 80, ECO is 554, Telnet is 587, and so on. There are many. You can see in the list. There's a list given at the end of this PPT. Okay. All right. So services can listen on this well known, like HTTP corresponding to this port 80. You can run HTTP process, which will listen to incoming packets. And then there are other ports between 1024 to 65535, okay, which can be given to client processes. Okay, so a set of, if you look at this set, some are reserved, some are unreserved. Okay, which can be used by any process. And now within reserved, you'll find various categories. Some are for TCP, some are for UDP, some are common. Okay, all right. So you can look at details if you're interested. Okay, in order to identify destination, we need IP address and port. Okay, first IP address says that which machine it has got to go to, and port says which of the process it has got to go to. Like, you have to give home address and particular person's name. Okay, so now this combination of these two, IP address and port, which is complete address in some sense, is defined as socket address. Okay, all right. So connection is between, whether it's TCP or UDP, is between a pair of sockets, right? So this is the IP address of this machine, and this is a port number 3470. So there is a process that's running at port 3470. So it could be any process, is communicating with maybe a one browser. Okay, is communicating with HTTP server, which is at IP address. Server's IP address is this one, and the port is 80. All right. Okay, so this we have already seen. So now TCP, UDP both will have source port number and destination port number. Okay, in their payload, in their packet, right? So this TCP packet or UDP packet will have header, and there will be two fields corresponding source port and destination port. Okay, and this will go inside IP packet, right? So this becomes part of IP packet, and the IP header will come here. All right, this we have already discussed, right? So this is another just pictorially it says that, right? So for every application that's running will have unique port, otherwise data cannot go there, right? So we say that the browser, this browser has port P1, this one email application has port P2, this browser, this host 1, this host 2, and this host 3, and we can say that, you know, we can define different ports for these, right? Like P1, P2, P3, and so on. So each one is connected to a port. Okay, all right, through network, and network is common, and each packet will have, of course, unique IP address and port number, right? So you can have one-to-one application, one-to-one connection, right? For example, this particular browser is communicating with one here. Okay, similarly, this email app is communicating with the app server here, but there can be one to many also, right? Because HTTP server may be serving to many requests because it's a server. So many client applications may connect to the same server, right? Okay, all right. So this is another view. So we when a client process wants to communicate something, it creates a socket. It will have source port and destination port. It creates a pack. So when it gives it to TCP, TCP will have a source port number and destination port number. Of course, then it gives to IP. Then IP will add corresponding IP address of destination, IP address of source, and other fields, right? Okay, all right. Please read about socket and socket programming if you have not learned it. Okay, so types of sockets. Sockets we have seen is basically API or interface. So application uses socket, and the socket internally uses TCP or UDP. Okay, so there have got two types of socket. One is corresponding to TCP, which is called sock stream. Another is corresponding to UDP. So this is for UDP and this is for TCP. Now TCP, of course, is reliable delivery. UDP is for unreliable delivery. TCP guarantees the packets are delivered in order. Although IP layer does not guarantee, but TCP guarantees this. UDP does not guarantee that packets will be delivered in order. TCP is connection oriented. UDP is not connection oriented. When we say connection oriented, it means that both ends have some state machine corresponding to a connection, right? For example, you are doing streaming of packets, right? You have switched on Netflix and doing streaming for certain period of time. Okay, this all the packets will corresponding to a connection or a stream. Okay, right? So the both end must know that packets have come or not come, and then many other things, right? Who is communicating and so on, right? So all these things have got to be known, and state of the connection is stored. Okay, TCP is bidirectional in the sense that when we create connection between two, the packets will go from one end to another and will also come back. Okay, while UDP, it can send or receive. It doesn't care, whether, receiver may just receive, or if it has to respond back, it may send UDP packet, but not necessary. Okay, but TCP has to be bidirectional. It means that if packet comes here, this side, there has to be something, some information will go, right? Whether I have received packet or reduce the flow and so on and so forth, right? Okay. Now, so now we have discussed about multiplexing, demultiplexing, and sockets, right? Now we'll come to TCP and UDP, primarily TCP, right? So when IP is communication between machine, one machine to another machine. Okay, and transport layer cares about the processes. It's between communication between one process to other process. All right. So because of addition of port number, we can identify process. All right. Okay. Okay. So both provide end-to-end services for app layer. Okay. All right. So now application normally don't think in terms of packets. Okay, application says that I have a byte stream, a stream of bytes, right? For example, your movie, and it has to be communicated. For application is just sequence of bytes, and other end should receive it and play. Or it application will think of I have a file to send, say file 1 to send. That's it, right? This is the way application will think. But now there has got to be some layer that will convert that byte stream into packets, fill into the packets, right? And then do further processing on top of that. All right. So for that we have these layers, right? Okay. Now if you want reliability, then we will just a minute. Okay. Okay. All right. If you want reliability, because some applications want reliability, some applications don't care about reliability, right? If the packets are dropped, just it doesn't matter, right? Just leave it. So now it may care for corruption if that somebody has changed the data or it got changed by some error on the way. All right. Or if there is overloading, you know, sender is sending at very high rate and receiver is not able to receive. Okay. Or in between routers are not able to receive properly. Okay. All these things have got to be taken care of by some this transport layer application, whether it's okay, is generally taken, reliability part is taken care of by TCP. Okay. All right. So all these things are done using something or other, some mechanism. For example, byte streams are converted into packets, and then reliability is achieved by what? Reliability is achieved by sending acknowledgements that I have received the packet. Okay. Now overloading in the receiver is achieved by limiting the data in buffer, right? If somebody is sending at very fast pace, then we'll say, okay, hold on, I cannot do it, right? Okay, for example, you know, you would have seen laborers, you know, when they work on the field, they throw one brick and other guy catches the brick, right? So if the guy is throwing at very fast rate, the receiver is not able to receive, then they synchronize, right? Similarly here, sender and receiver, they don't know each other. You know, when you're sending your packets to Netflix, do you know each other? You don't know. You have never seen them, right? But there must be some mechanism that your if you know the if server is able to send, is sending at very fast pace and you're not able to receive, then you can message it that I'm not able to receive, right? So please reduce the rate. Okay, that's called flow control. So TCP has mechanism for flow control, right? And similarly, if in between routers are congested, then there must be a way of controlling that. And if single bit error happens in the packet, right, TCP part, this is TCP or UDP part, their single bit error should be detected. Now, why this assumption? Single bit error. So there is checksum to find out if there is single bit is flipped. It could, the reason is that normally, you know, error rates are very low nowadays. Okay? So because quality of networking has improved over time, so single bit is generally good enough to find out because of some error on the way, right? Single bit is flipped. So now basically transport layer provides a logical connection between two entities from one app to another app, one application to other application. It provides a way. Application don't care about what kind of network you are using, whether you are using Ethernet or whatever. Okay, you are using, so it just wants its bits to reach the other end. Okay, so now what sender will do? Sender will look at the data from app and break into segments. Okay, from TCP packet, put the segments into TCP payload or UDP payload and give it to IP. Okay, all right. So we have TCP, which is reliable congestion. It does congestion control, flow control, connection setup, and UDP, which does unreliable on-order delivery. Right, it's a no-frill, batch-buffered IP. Okay, only thing it does is multiplexing, uses port, multiplexing and demultiplexing. Basically, use of ports. That's it. Okay, but both of them don't guarantee delays or bandwidth. You know, nobody says that how whether you are streaming it from Netflix or whatever, it does not guarantee that packet will reach you in say 10 milliseconds. Okay, now it is responsibility of those service provider to make sure that packets don't take too much time. Otherwise, you will not watch IPL on OTT. You will watch it on maybe TV. Okay. The reason for that they have normally servers now very close to your home somewhere. You know, in Bangalore, for example, uh, Netflix may have a server. Okay, all right. So let's come to TCP. Basically, internet is unreliable, and if you want reliability between two ends, you will have to no other way but use TCP. Okay. Now, so now we are solving here many problems. So because IP packets have limited size, IP packets have limited size, right? And what you are getting is stream of bits. Okay, so now what the TCP has got to do is that it has to split the bits, set of bits, and put this into TCP payload part. Okay, attach header and send it to over IP. That it does, right? What happens is packets arrive out of order. The IP packets may take different route, arrive out of order. It has to somehow reassemble them back. How can it reassemble them back? Like, you know, many of you are going from IIT Mandi campus, command to a city, and you are in a restaurant, and then restaurant guy says that, you know, you have to come in order, first, second, third. So you guys have some slip 1, 2, 3 or whatever, and you take different route, reach out of order, but you have numbering. The guy at the other end will reassemble you, will say that, okay, first guy first, second guy second, third guy third, and so on and so forth, right? Whatever path you have taken on the way, but at the end, corresponding TCP will put everything back in order. What happens if somebody is lost on the way? If packet is dropped on the way, the receiver will know that something is dropped, right? So it will not send X for that. Okay, it will keep sending X for previously received packet, like 1, 2, 3, 4. 4 guys are there. Okay, and then first guy has come, second guy has come, fourth guy has also come, but third has not come. Then this hotel guy will say, okay, I have received up to 2. Okay, now receiver sender will then send 3 back. Okay, something like this. Okay, all right. So it does byte stream abstraction that we have already discussed. So bytes, you receive nothing but application thinks only in terms of bytes. Stream of byte, like, you know, your water in a pipe. It has no boundary, right? I mean, you continuously water will flow in, right? Similarly, stream of bits will continue to come here in the pipe. Okay, at the other end, same thing we should be received. Similarly, stream of bits are coming, you will have to just pack them into packet. Okay. So these points we have already discussed. It provides ordering, it provides reliability. By sending acknowledgement, it will explicitly send X. Okay, all right. So these are point to point. It means a TCP connection exists between two endpoints, sender and receiver. Okay, it will not happen between one sender and multiple receivers. It doesn't. Okay, so many of you are watching Netflix, or nowadays you are doing Geo Cinema for IPL. Do you think that same packet is being, if two of you are sitting close to each other, same packet is forking out and going to both of your machines? No. Okay, in this world, OTT world, there is a one-to-one connection from your machine to other end. Okay, the individual connection. Okay, full duplex data means that data travels in both ways that we have seen. Cumulative X, you have received, segment 1, 2, 3 in line. Then you'll say segment, you'll say that 3 is received. I am expecting 4. It means that 1, 2 has already been received. Okay, like when you are going to a restaurant with your numbers 1, 2, 3, 4, packet is a person number 1 to arrives, that the hotel guy will say that 2 is up to 2 is received. I am expecting 3. So it's a cumulative act. Pipelining, it means that when all of you are going, then it's not that understanding is not that first guy will go and reach there, only then this will send the egg for first, only then second packet will go or second person will go. Okay, so in pipelining, one after other person can follow each other, right? So one packet after other will flow on the way. Okay, and then packets are received at the other end and then acknowledgement is sent back. Connection oriented is essentially handshaking between two ends. So they must be managing some state machine. Flow control is that your receiver will say, "Yeah, slow down. I cannot handle it. You are sending at very fast pace. Just slow down." Okay, so some way of controlling the flow of packets or number of packets, right? Okay, applications are, most of the applications today that you use TCP. Now this is one. There are two protocols in that in a communication world, not necessarily in TCP, is stop and wait and pipeline. Stop and wait is something that first packet goes from one end to another end. When it is received properly, then it will send ACK. Only then second packet will travel. While in pipeline one, sender will send packets after packets, right? Because this path or link can carry multiple packets one after the other, depending on the bandwidth of the pipeline, right? And similarly, X can come this way, right? The first packet received, the X will come, then second packet received, X may come, and so on and so forth. Or cumulative X can also come. So TCP uses this pipelined way of communication. Okay. And then we have principle of it. So what? Okay, this point we already discussed. Whatever is happening in IP, TCP provides reliable communication. So this application have not got to worry about problems of IP or IP network, right? It says, it assumes the moment the application is using services of TCP, it will know that data will be delivered properly to other end, reliably to other end, right? Okay. However, what happens is that sender doesn't know about receiver, right? Okay, yet it means that there is, you don't know where the Netflix server is, right? But you have understanding, you're using the same protocol, so you can still, you have to just follow your protocol and then reliable packet transfer can happen. Okay? All right. So now we have byte stream abstraction, wherein sending process just send bytes, stream of bytes, and other end receives them. This is the this is what application think. It's like, you're putting water at one end, it comes out other end. This is, instead of water, you have stream of bits. In the same order, it comes out. Okay. So internally what we have a buffer, and then we keep filling bits here and then keep sending them in, take some of these bits, put them into TCP. They will come here in TCP and put header, TCP header like port number, etc. And this will go over IP. Okay, and will reach to other end. And other end will take this out and fill that in buffer, and then receiving process can read it. Any question up to this point? Okay, are you able to follow it?
Yes, sir.
Okay, so this is another abstraction. So I have given a lot of pictures so that you understand properly. This app at one end is sending it. It only outputs stream of bytes. So it's just sending these bytes in this order. It goes to TCP layer. TCP puts this, takes some of this that we call a segment. Put this inside. Put this segment into TCP packet. Put a header. Okay, and then this header goes as a payload of IP packet. Okay, all right. So sorry, this IP protocol, and then this will go inside IP packet. So this is the TCP packet, goes inside IP. So IP will also header. This goes to other end. IP protocol will handle it. Okay, take TCP packet out and give it to TCP layer, and TCP layer will look at the port number, etc., and give it to port number correspond to this this particular application, and then pass it on as a byte stream to this application, right? So bytes here are received as a byte at the other end. Internally it goes over TCP packets, and TCP go inside IP, and IP of course goes inside layer 2, which is maybe Ethernet or whatever. Okay, so and application will see a stream of bytes like here, byte 0, 1, 2, 3, etc. This is a time t0 and so on, and it will be received after some time in the same order at the other end. Okay, but in order to achieve this, what we are going to do is that take some bytes from here, say for example byte 0 to byte 80, put this into TCP data part, and and of course there will be header, etc., which I am skipping it now, and then it will receive it at other end, and then again byte stream is created. Okay, so what we see is that this is IP packet, and this is the actual application data for byte streams, right? We call it segment. Add to segment TCP header, put this in, then when it goes to lower level, then IP packet is created and IP header is added to that, right? And there are various terminologies associated with IP can handle up to some length, right, which is called MTU, maximum transmission unit. Okay, now of course how much IP can handle also depends on how much Ethernet packet can handle. For example, 1500 bytes is the maximum for Ethernet. Okay, so now from this we can find out what is the TCP segment size in general, right? Okay, so TCP segment size is called maximum segment size, no more than, so we from this we define what is the maximum segment size then TCP can handle. Okay, which is generally maximum MTU, maximum transmission unit for IP, minus IP header minus TCP header. Okay, all right. Okay, don't just go through it once and you will know. Simple, right? So basically, whatever be byte stream here, it will go as part of segments, will reach to other end, and they will reassemble back, and you get the data back or stream back, right? So TCP packet looks something like this. It has source port number, destination port number, corresponding processes, then sequence number. If you don't have sequence number, then we cannot reassemble the packet, right? Okay, if they go out of stream, etc., out of order, then you cannot put these packets one after other, right? Now, here the sequence number does not belong to the IP packet number or TCP packet number. It belongs to, it basically shows the byte number. We'll look at that later, right? Okay, ACK is when you the sender sends something, receiver receives it, then it has to ACK it, right, or acknowledgement. Okay, now the field here gives the acknowledgement number, what up to what byte it has received, and this number is valid if this flag is valid, right? If this flag is set to 1, only then this number is valid. Okay, this is application data. It means that your byte stream will come here. Okay, all right. Then of course there is a checksum to find out if one of these byte, one of the bit is flipped. Okay, all right. And then we have length, header length field, because the header length could be variable. Okay, and then we have receive window. Basically, this is required for flow control. So receiver will say how many bytes I can receive. Okay, this is called receiving window. Now, if sender is sending at very fast rate, then we'll say then receiver will put a number here that this is going to my receive window, and based on that sender will control the flow. Okay, apart from that there are some flags which is called R, S and F. R correspond to RST. It means that if TCP connection that is created end to end is to be reset by either parties, okay, or terminated immediately, then this flag is set. It means that now this TCP packet is indicating that now after this I will not, this connection is over. Okay, SYN is required for setting up the connection. FIN is again for transmission, but is more handshake way, I mean, in the sense that both ends will agree on termination of connection. Well, RST is simply when either party sends it, means that okay, I am just breaking it up because of something. All right, so these are the fields of TCP. Okay, so in general we can say now any connection is defined by source IP address, destination IP address, source port number, destination port number, and because all these can be TCP or UDP, we'll have to say whether it's a TCP or UDP. So now you say TCP with source IP, destination IP, source port, and destination port. This defines complete connection. Okay, all right. Okay, any question up to this point? Okay, all right. So let's stop here. Okay, and then we'll look at what these sequence numbers are. Okay, and how TCP works on this sequence number. Something on initial sequence number is there to avoid some kind of attacks. Okay, and how this sequence number will be used. Okay, so we'll look at some of these concepts in the next class, and then we will study what kind of threats TCP can have. All right, now note that this protocol is not easy to understand, right? So what we have done so far discussed is very simple concepts. Okay, so I will take one more class to discuss TCP. Okay, and then I need one class for TCP vulnerability, one class then for reliable protocol. Okay, TLS protocol, and then two classes for crypto. if you're interested in knowing crypto and blockchain. So I need 2 extra hours from you if you're interested in learning these topics. If you're not, I am fine with, completing whatever I can. Okay, because we have lost possibly one lecture in between, because we had one mid-sem exam, I think, on the first quiz on regular class day. So ideally, we should have 42 lectures. We'll be completing 41 plus 2 extra lectures I need. Okay, who can tell me when we can have extra classes? Or you don't have time for it?
Sir, actually, for the end, while floating for the ensign slot, I floated the form, but actually,